Start video. Taylor is with us. Yay.
Hey, how's it going?
Hey, terrific. It's a beautiful day out there, looks like. October 1st. Let's see if we got anybody else with us here this morning, Taylor. Oh, yes, we got a good crowd. We have Alex and Daniel and Julian and Dawson and William. And Bryce and Brian, Tyler and Taylor, Reagan. We got a nice crowd here for Thermo. And it's time to start. Did anyone have a question for me before we begin? Well, okay. Go ahead and ask if you have something.
Mr. Griffin,
Yes.
I'm just only confused on problem 4105E. How we're supposed to gonna draw the PV diagram on that?
Tell you what I want to do, Mohammed. I want to do one just like it.
Mm-hmm.
And I bet you after we get through with this one just like it, it's a nozzle.
Yeah.
It's an English problem with a
Yes.
nozzle.
Yes.
And then I bet you can do it.
All right.
I
that works.
fun by doing that specific problem.
That would work
Now,
for me.
what Mohammed's talking about is the homework assignment number 13. It's 4105E. It's a nozzle. And it's due Sunday. Today is Thursday. It's due Sunday. Okay. All righty. But what I want to do is I want to do one just like it, a nozzle with English values. And this is problem example 4.4e. Let me see if I can find it. 4.4e, okay. Right, I found it. Here's what I want to do on page 121. Example 4.4e. I want to do it. This should help Mohammed and the others. Now this is steam. We're talking H2O here. Steam at 0.6 megapascal and 200 Celsius. Comes into a nozzle. Well, why don't we draw that? See, here's your nozzle. And here comes this steam at 0.6 megapascals, 200 Celsius. And it has a velocity of 50 meters per second. Now it leaves at 0.15 megapascal. With a velocity of 600 meters a second. Hey, it speeds up. They want to know the final temperature and the quality if it's inside the vapor dome. Well, we can do it for it. Now, I'm not going to peek and look at the answer. See, this is what you guys should do. See, they have examples in your book. I'm going to take a piece of paper and I'm going to cover up their answer, and I'm going to see if I can do it without peeking, without looking at their answer. And then when I get all through, what I'm going to do is I'm going to pull the paper down and see if I did it right. Do you guys do that? You should. It's a great way to study. Okay. Well, let's start by reviewing our first law of thermodynamics for control volumes. The way it works is if you have a control volume, which that's what a nozzle is, a control volume. It has mass going in and mass going out. So it's a control volume. And the first law for control volumes goes like this. Hey, I just barely had enough room to write that. You should know the name of everything on there. This here is the first derivative with respect to time of your total energy inside your nozzle in this case. This here is the heat transfer rate, either from or to the nozzle. This here is the power either produced or the power exerted on, in our case, the nozzle. All three of these terms are zero. This nozzle is what they call steady state. In fact, this is the steady state version of the first law. SS stands for steady state. The energy inside this nozzle, the total energy, that's what E is. You could put total there if it makes you happy. It's constant with respect to time. An hour later, it hasn't changed. A day later, it hasn't changed. That is, unless somebody turns off the flow. But as long as the flow is the same, the energy inside is the same. On nozzles, they're adiabatic. They don't exchange energy by heat or work. There's no work either. Nozzles don't do any work. The MI and the ME are exactly the same. If they're different, you got a problem. But in steady state, whatever mass flow rate going in is equal to mass flow rate going out. Nozzles don't go down the road any. They don't have any velocity. I take that back. This is the nozzle itself doesn't have any velocity, but the steam coming in does. This is the incoming velocity of the steam. That's a keeper. This term here you can throw out for our nozzle because it's not going up or down. You can throw out the exiting specific gravitational potential energy because it hasn't changed its altitude any. Whatever the altitude is of the incoming steam, it's the same. So there's no change in gravitational potential energy. When you get all through, since these are the same, you don't need an I and an E. You can do some algebra. And you can lop those off since they're the same. And what you'll have is this here. And you're done. It's a lot nicer to write it like this. In fact, this is the first law of thermodynamics for nozzles. Each kind of device has its own first law. Do you understand? This is the general first law that applies to all control volume devices, and particularly to steady state devices, because this will become zero if it's steady state. If it's not steady state, that will not be zero. But this is a particular first law of thermodynamics for nozzles. So we had a little review there. We talked about the different terms. I didn't tell you what that was. That's got a name. It's called the incoming specific enthalpy. This whole term here is called the incoming specific kinetic energy. That V there, if you're just looking at that V sub I, that's the incoming velocity. See that V sub I? That's the incoming velocity of the steam coming into the nozzle. And this is the exiting, see that little E there? That's the exiting velocity of the steam leaving the nozzle. This whole term here is called the specific gravitational potential energy. It's got a big name, doesn't it? G is, of course, the acceleration of gravity, and that Z is the up and down coordinate of, in this case, the incoming steam. But see, it doesn't go higher or lower, so these will both be the same, and you can just get rid of them. Okay, well, we had a review over our first law, and back to our problem now, and we're going to solve it. And you know the procedure. You draw a device sketch, and I did. Look, I drew the device sketch. That's a nozzle. And we're going to draw the PV diagram. Now, I think this is what Mohammed wanted me to do on that other one. But you know it's going to look like that because it's water, it's H2O. And we've got 200 Celsius coming in. Well, see, 200 Celsius is somewhere up here. There's 200 Celsius. Now we're going to go to our tables, and we're going to see what this pressure here at 200 Celsius is. Help me find 200 Celsius. I did, and I found the pressure there is 1553. 1553 point something. Point 8. 0.8 kilopascals. But wait a minute. What we have is 600 kilopascals. Well, you know what? 600 kilopascals is a heck of a lot lower. It's down here someplace. Here's your state one. See, this is 600 kilopascals. We're out here in the, when you're in superheated vapor, you go to the superheated vapor chart. Help me find 600 kilopascals. I did. And 200 Celsius. I did. There it is.
Mr.
I can
Griffin,
write down. Go ahead.
we did this problem last day on Tuesday.
Oh, thank you for telling me that.
Yeah, I think it's on the next page, the 44.4E. It's on the next page.
So what you're telling me, Mohammed, is we solved this problem already.
Yeah, on Tuesday we did that.
Thank you so much. I'd forgotten. Please, all of you, please forgive me for wasting your time.
I was enjoying it.
But we did this already. Okay, good, excellent. Well, that should help you a lot, Mohammed. If I remember right, yeah, it's coming back now. We actually entered the vapor dome here. Yeah, thanks for telling me that. I'm gonna give you a big fat thank you point. I appreciate you so much. It turned out that we had I remember now, it was something like 90% or something like that. It was, or 98%, I don't remember, but it was way the heck over here. And we solved it. Good. I'm so glad. Okay, we did that. We don't have to do it again. Let's do a different throttle. We're going to do a throttle, but we're not going to do that one anymore because we already did it. But that first part I told you, that review, that was good. That wasn't wasting your time. So here we're going to do a different. Now wait a minute. We're going to do a throttle now. That's different. See, this was a nozzle. We haven't done any throttles. The topic right now is throttles. Now, back when I had my first car many years ago, it had a throttle. It did not have fuel injection. Cars did not have, my car did not have fuel injection back then, back in the late 50s. It had a throttle. But I'll tell you what a throttle is. It's in your chapter here. Let me draw a picture. Here's a picture of one. It's just a constriction. It's like a pipe with a constriction. And see, here comes the flow. The flow's coming in, and it's what they call laminar flow. And it hits this constriction. Looking at it from this way, if you look down this pipe, what you'll see, it's like a washer. It's like somebody has welded a washer in here that has a little hole in it. And when the flow comes in, it swirls around and creates all this crazy disturbance here. It's not laminar flow anymore. And a strange thing happens. The pressure goes down and the temperature goes down. It's a throttle. Now, the reason why I had a throttle in my first car was when that pressure goes down, they had a gas line coming in here, and it sucked gas because of the low pressure. It would suck, it had a vacuum. See, it creates a low pressure, and that vacuum sucked that gas into my intake manifold. And the thing was, I could adjust the throttle. It was called a butterfly valve. When I pushed on the accelerator, it was actually a butterfly valve that I could adjust different positions, different angles. But never mind that. You don't care about that. Their picture, what they have for their throttle is on page 123. And it's just a constriction, like I was telling you, of some kind. There's different ways to make constrictions. And when you write your first law, you go through all those terms. I shouldn't have erased it, but it's a steady state device. This is 0. This is 0. This is 0, just like with a nozzle. It turns out that the velocities don't change like they do in a nozzle. And so you don't really need those terms. Because none of them change. This is the simplest kind of device. It turns out when you get all through with your first law of thermodynamics, for a throttle, the HI will equal to HE because these mass flow rates have to be the same. And these are the same. These are 0. Hey, that's it. You are looking at the first law of thermodynamics for a throttle. Now, do they have that in your book? I'm looking, trying to find it here. I don't see it. Well, I can't find it right now in your book, but that is the first law for a throttle, and we're going to work one. By the way, they have a name for that. I don't know if I told you that. That's called isenthalpic. It's an isenthalpic process. What that means, it's constant enthalpy. Okay, well, let's do one. This is problem 424. I don't think we've done this one. I hope not anyway, because I don't want to repeat stuff if you don't need it. However, repetition is good. Now, this happens to be methane. So let me find it. Help me find problem 424. It's methane. All right, I'm getting close.
Page P-38.
Yeah, I found it. Methane. Okay, here, let me write this stuff down here. I hate to erase that. That's such a wonderful equation there. But it says that we got 1 megapascal coming in. I need the room. Memorize that. That's our first law. It's very, very important. We got 1 megapascal coming in. Methane at 250 K. All right. Throttle to a valve to 100. Coming out, it's 100 kilopascals. And they want to know the exit temperature. We'll put that in kind of a mystery cloud here. We'll solve it for them. Okay, well, let's go to the back and we have a methane table. Let's find it. We're looking for methane. I'm looking for methane in the back. Trying to find methane. Having trouble. Hey, I finally found it. Methane. Now what let's draw our PV diagram. Here we go. PV diagram, methane. Now we're at 250K. Well, you know what? The top of the dome is 190.6K. So that must mean that 250 is up here someplace. Yeah, there's 250. Now we have 1 megapascal. You know what? That's 1,000 kilopascals. That's kind of in the middle here. State 1. That's your incoming. State 1. Incoming 1,000 kilopascals are coming in right there. And we're going to look up in the superheated vapor region table, 1,000 kilopascals, 250K. And we're going to look up the H. We could look up all the stuff. We could look up V1. V1 is 0.12541. See if you can find this stuff. H1 is 50601. 50601. See if you can find that stuff in the tables for methane. And I'll wait till I hear a couple of uh-huhs. Can you guys dig around in your methane table? Now, some people call it methane. But I don't like that, methane. I call it methane. I want to hear an uh-huh that you can find those in your tables. I'll wait.
Uh-huh. Uh-huh.
One. Need another one.
Yep.
Yep, good, excellent. Okay, now here's the dirty little secret of the throttling process. The H1 is equal to the H2. They call that isenthalpic, constant enthalpy. So now I know what H2 is. It's 50601, the same as H1. Well, so what? But see, this is at a lower pressure. P2 is 100 kilopascals. So let's see if that's in the superheated vapor. I bet it is. 100 kilopascals. And what we need is 50601. Yeah, it's in there. All we got to do is interpolate. I need some room to interpolate. Here, let me make some room. I'm going to make some room here.
I'm sorry, was V1 and H1 from the superheated or the saturated table? I don't know.
No, it's superheated. I know that because the 250 Kelvin is hotter than the critical isotope. Who was it that I was just talking to?
This is Nathan. I'm just not seeing those numbers on that table.
Nathan,
I'm not seeing
the
those numbers either.
critical isotherm, I'm so glad you asked, is 190.6. They call that the critical isotherm. It comes down here and just glances off the very top of the vapor dome like that. It has an inflection point, and that's 190.6 according to the vapor dome table that you just mentioned. You said, well, do we look it up in there or do we look in superheated vapor? Well, this is the critical isotherm, but we're hotter than that. We're 250. 250 is hotter than 190. And so we're out here. You can't enter the vapor dome if you're out here. So you go to the superheated vapor. Nathan, did you understand me?
I do. So I'm looking at the superheated table now, and I'm looking at 250 degrees Kelvin and 100 kilopascal.
And
Wait, 1,000.
You want-
I'm sorry.
Nathan, you want to look up
1,000.
you want to look up one megapascal, which is 1,000 kilopascals, in the superheated methane table.
Yeah,
I made
that
the
was.
same mistake, Nathan.
Yeah. Okay, we're good now. We were looking at 100, I think, instead of 1,000.
Right.
Stupid
Right.
mistake.
You look up 1,000. But we're
Got it.
okay. Okay,
We're
we're happy.
okay.
Everybody's okay, except me. I'm not okay because I got lost. What are we supposed to do now? Let's see.
We were going to interpolate.
Oh yeah, we're going to interpolate. That's what we're going to do. Now here's the stuff we know. We know H2 and P2. So help me find the 100 kilopascal. And then what we want is 506. And I tell you what, it's there. We just have to interpolate. Now here we go. There's some room here. Now the H goes from 464.99 at 225 Kelvin to 250 Kelvin. And the H there is 518.27. Now this is all at the 100 kilopascal. See if you can find that in the superheated vapor methane table. And see, what we want is 506.01 kilojoules per kilogram. We have to interpolate between here, and we'll have the answer. So here goes, everybody. Get your calculators and interpolate between. I'm trying to find what this mystery is here. I'm trying to find the temperature. This will be T2. Go for it. Well, I got an answer for a T2. I got 244.2 degrees Kelvin. But I'll give you a little more time. I'm hoping that you can get that. Anybody agree with me on that?
Yes, sir.
Yeah. Well, we're done. I think that's what they wanted. Let me see here. Let me read this problem. We just did 424. It's a throttle. 424. What's the exit temperature? Well, that's what we got. Now let's look. I got an answer book here. We'll see what it says. I got an answer book, and this is 424. And it says, uh, 244. That's what they said. The answer book says 244 K, and that's exactly what we got. Now, I didn't draw it here. We better draw it. Now you see 244 K. I'm getting lost here. What? Oh, that's the critical temperature. We're right in here. Not much room for me to squeeze this in, but I'll try. 244. 244K is bigger than 190, which is the critical temperature, but it's smaller than 250K, which is our starting temperature coming in. See, we got 250 coming in. It cools off, not much. It only cools off, what, 6 degrees? But it's colder, and the pressure is a lot smaller. The pressure is only 100. So it goes, there's your state 2. I didn't draw that great, but the specific volume increases. We never got a specific volume, but we could. All you'd have to do is interpolate, write the values in here, and find, interpolate. They get bigger. Specific volume gets bigger. Temperature goes down, pressure goes down. That's what always happens in the throttle. Well, good. We did a throttle. Well, let's do something else. How about, let me see what I want to do the best here. I'm thinking of turbines. I'm thinking we'll do a turbine. So let me decide here. Yeah, we'll do a turbine. That's what we'll do. Okay. I'm going to erase all this if you guys are happy. Do you have any questions on that throttle? I think there's a throttle on your homework. Okay, well, let me erase all that, and we'll talk about turbines now. And we'll want to do a turbine. Let me find one here that would be kind of fun to do. Okay, I don't want to do your homework though. Let me double check. I don't want to do your homework if I can help it. Okay. Yeah, this will be okay. We're going to talk about turbines now. Now back to this first law. I keep rewriting this and erasing it. Getting kind of lazy there. Okay. Now, turbines are essentially adiabatic. I'm lying to you a little bit because they get hot and they do irradiate some heat. They have a heat transfer, but it's an insignificant term. We're just going to assume, we'll work a turbine problem here in a minute. We'll assume that's zero. It's a steady state device. The symbol for a turbine is a deal like this. This is the schematic symbol for a turbine. You got an M dot coming in and an M dot going out. You can put a little I and E there, but we're going to be dealing with steady state turbines right now. You see, when you fire it up and you're starting up the turbine, that's not steady state. But once the thing achieves all of the pressures and temperatures you want, and the mass flow rates that you want, that they're all constant, and the energy doesn't change with time inside your turbine. But this time we don't put a zero on this one. This is the power. And that's the reason why you have the turbine. Turbines provide power. So we don't get to cross that out anymore. And then you have an M dot I and an M dot E. They're going to be the same on these simple problems. However, you can have more complicated problems with maybe 2 entrances and 2 exits, or maybe 3. And so you'd have more terms there. You could put a sigma right there. You with me? But we're going to keep it simple. We're just going to have 1 input, 1 exit, mass flow rate be the same. Now, on the problem I was going to do with you, they include the velocity term, but they didn't have any specific gravitational potential energy term because it didn't go up or down. It's in a building. You go in this building, you open the door, and there's a loud noise, okay? These things make noise. Close the door, you go have your coffee break, you come back, you open the door. Guess what? It's making the same noise because it's a steady state device. If you look at all the gauges there, the pressure here, temperature here, a couple hours later, they're the same. Nothing's changing with time. Now, stuff changes with location. You'll find with turbines, they're kind of like throttles and nozzles. The pressure here will be lower. The pressure changes with location, but not with time. Whatever the pressure is coming out, an hour later, it's the same. Okay, and don't forget you got your M dot here, but the E and the I are going to be the same on this problem. And let me see if there's any, on this one, they said the exiting has very low velocity, so you don't need any other terms. So that simplifies it a lot. What I want to do is problem 425. I'm going to do problem 425. It's not on your homework. It's a steam turbine. It's H2O. It has an inlet of 3 kilograms per second. So your M dot is 3 kilograms per second. Here it comes. We know what the incoming mass flow rate is. 3 kilograms per second. It's coming in at 1200 kilopascals. Let me write that down. 1200 kilopascals and 350 C. Guys, I'm doing problem 425 right now as an example. Oh, gee. We're okay on time. We're here till 12:20, aren't we? Yeah, we're going to make it. Okay, let me keep reading. And the velocity is 15 meters a second. Coming in, we have 15 meters a second. The exit is at 100 now and 150 C. They said very low velocity. That's how come I didn't include the exiting velocity. So you could just say the exiting velocity, call it 0. Very low velocity. Now what they want is the specific work and the power. They want us to find this. Let's put a little mystery cloud around that. Well, actually, no, they want us to find little w. See, the way it works is big W dot is equal to m dot times little w. Do we know it? We know m dot. Let me circle that. They want us to find little w. Okay, well, when we do, we can find, well, actually, I think we're going to find big W dot, and then knowing m dot, we can get little w. Because see, this is called specific work or work per mass. It's equal to your power divided by your mass flow rate. They gave us the mass flow rate. We're going to get the power from the first law. We know m dot. Let me circle that. Hey, we know the incoming velocity. Let me circle that. It's 15 meters a second. We know m dot. It's the same exiting and coming in. If we can only get, look here, if we can only get the incoming and exiting specific enthalpies, we can work this problem. Well, what's next? We did our device sketch. And then, you know the drill. We have to do a PV diagram. It's water, so you know it's going to look like that. Now help me find 1200 kilopascals, 350 C. Well, see, 350 C is way the heck up here. (350°C), because I happen to know water, the critical temperature is like 372 or something like that. And this pressure here, we're going to look it up. 350°C, help me find it. We're looking up water now. 350°C, and it says 16,514. This pressure here is 16,514 kilopascals. We just have 1,200. You know what? 1,200 is smaller than 16,000. It's down here someplace. 1,200. So that means we're out here. Superheated vapor. Go to the superheated vapor chart and look up 1,200 kilopascals. (350°C). Let's see if we can write down some stuff. Little v1 is 0.23452. We could write down all this stuff if you wanted. Little u1 is equal to 287,216. Little h1 is equal to 315359. And little s1, well, we don't know what that is yet. That's a specific entropy, and we'll learn about it eventually. Okay, well, look at here. Ta-da, I just got that. See it? What does it mean in this class when I circle something? It means we know what it is. You know what? If we could get this little exiting specific enthalpy, we can solve for the power. Well, how would we do that? Well, they said it's 100 kilopascals. Look it up. Go to your tables and look up 100 kilopascals. 100 kilopascals. And 150 C. We're in the superheated vapor. We're out here someplace. Yeah, there's your state 2. I can write down all kinds of stuff. Little v2 is equal to 1.93636. I could write down little u2, it's equal to 25875. Little h2, is that showing up on the, yeah, it's showing up. Little h2 is 2776.38. There's state 2. There's your process. It's out there in the superheated vapor region. And hey, I just got this. Look here, I got everything I need. Now let me put the numbers in. Okay, we got a 0 here. Equals 0 minus the power plus 3 kilograms per second times 3153.59 kilojoules per kilogram plus, don't forget the parentheses now, plus the velocity, which is 15 meters a second. You have to square it, divide by 2. Now, we're showing you guys this the other day. You got to divide by 1,000 because a meter squared per second squared is equal to a kilojoule. No, it's equal to a joule per kilogram. And what we want is kilojoules per kilogram. So you have to divide by 2,000. Then we'll subtract 3 kilograms per second times the 2776.38. Oh, I ran out of space. Just barely got that in there. Okay, we have a wonderful equation now. I hope you can read my writing. It's pretty sloppy. We're going to put in all these. There's only one unknown, and that's the power. We know all these other numbers. I'm going to do it. I want you to do it, and we're going to solve for the power. Here goes. Well, I got an answer for the power. I'm a little confused about the units, but we can figure it out. Think about it. If you have kilograms per second times kilojoules per kilogram, you get kilojoules per second. You know what that is? That's a kilowatt, isn't it? A kilojoule per second is a kilowatt. So I think I have the power. Let me tell you what I got. Hey, Derek. I'm doing great. I'm right in the middle of a class. Hey, class, say hello to Derek.
Hi, Derek.
A bunch of them forgot to unmute. Let's try that again. Unmute and say hello to Derek.
Hello,
Hello,
Derek.
Derek.
Hey, Derek.
Hi, Derek.
A lot
Hey,
of
Bear.
these students know you. Yeah. Hey, call me back. I got to finish this class. Yeah. That's another wonderful instructor at TCC that some of you guys might be lucky enough to have. Okay, now let's see. Oh, I did this. And I got a value for the power equal to 1, round it off, 1132. Did anybody get 1132?
Yes.
Now, I think what that is a megajoule. Because, no, it's a kilojoule. It's 1,132 kilojoules. And see, that's equal to m dot, which is 3 times little w. So if you want little w, here, let me get little w, and then I'll look in the answer book and see how we did. Little w, what that is work per mass. And if you take 1132 and divide it by 3, you get 377 something kilojoules per kilogram. Now let me look at my answer book. Just a minute. I got an answer book here, and this was problem 425. We're trying to do 425, and they said that's not, yeah, that's what they got. Yeah, we got the same thing they got. The answer book says 377.3 kilojoules per kilogram. We did great. Yay, we did good. So we just did a turbine. Did you have a question on that turbine? Anybody? Because if we're okay, I think we got time for another problem.
Where did you get the V2, U2, and H2?
Oh, thanks for asking. We're going to show you where we got that. They said the exiting pressure was 100 kilopascals. So go, now who am I talking to?
Alex.
Alex, go shopping around in the water tables, in the superheated vapor water tables, for 100 kilopascals. I'm on table, Alex, I am on table B.1.3.
Oh, okay, I found it. There we
Yeah,
go.
good for you.
They're not mystery
Anybody
numbers
else?
anymore.
Anybody else have a comment or question on anything? Well, I guess not. I guess you're okay. We did a turbine. That was fun. We probably should do a turbine with the Inglés, senor. Let me find one here. Find a turbine with the English. Let's see here. Yeah, here's one. Yeah, this looks pretty good, but I don't want to give it to you if it's on your homework list. That would spoil your fun. Let me see. Let me check that. Yeah, I think it's going to be okay. Yeah, okay. Well, let's do it. Let's do a turbine with the English stuff. I'm going to erase everything if you're happy. All right. I'm going to keep that first law, though. We'll try to keep that up there. That right there is your first law of thermodynamics for devices that have mass flow rates in and out. And right now we're going to do one with the English units. This is a turbine. It's problem 4.110E. Liquid water turbine receives 4 pounds of water, blah, blah, blah. Now, you draw the device sketch. Here goes. We're going to draw the device sketch. And this happens to be a water again. The M dot's coming in. That's a mass flow rate is 4 pounds mass per second. 4 pounds mass per second. At 300 psi and 77 Fahrenheit. That's kind of room temperature, but that's pretty high pressure there. A velocity of 50 feet per second. The exit is at 15 psi. See, you can put a lot of stuff on your device sketch. And 77 degrees Fahrenheit. They said very low velocity again, so we'll just say the velocity is dang close to 0. Same problem. They want us to find the they want us to find the little w and the power. They want the little w and the big W dot. They call this the power, and this is the, well, they call this specific work. I prefer the term work per mass. It's the same thing. It's work per mass. Now the name of this is power. Remember, that's the whole purpose of having turbines. The purpose of nozzles. Here, let's have a little review here. If you got a turbine, the purpose of the turbine is to produce this big W dot. What that is work per time. That's what power is. Did you know that? Power is work per time. That's why you have it. Now, does anyone remember the purpose of a nozzle? Let me go to one of my excellent students here. William, unmute and say hello, please.
Hello.
William, what is the purpose of a nozzle?
I have no idea.
I love those honest answers. This is your lucky day, William, because I'm going to tell you, and then you'll have more knowledge than you had before. See, if I'd asked somebody that already knew, then they didn't learn anything. They already knew it. William, the purpose of a nozzle is to speed up. See, I've got a nozzle on my garden hose. I screw it on my garden hose and I go out there and I turn on the water. Now, if I don't have that nozzle on there, the water just kind of goes bloop. It doesn't go very far. But if I screw that nozzle on there, it shoots out. It speeds up. And that way I can squirt my rose bush. Now you know what nozzles do. Now, turbines. Let's see if William can get this. William, the purpose of a turbine is what? Why do we have turbines? What's the purpose, William?
To create power.
That's it. He got it. Good going. Good going. The whole idea is to create power. That's why we have turbines. You know, they have different kinds of turbines, but that's what they have. They all produce power. Okay, well, let me erase all this jazz. And let's get back to our problem. We're never going to make it. We're running out of time here. When does this class end anyway? At 12:20? Oh, gee, we only have 13 minutes. But you can do a lot in 13 minutes. Now, we did our device sketch. What's next? You would never, ever forget doing this for me, would you? No, you would not forget that. We will always be doing PV diagrams. Sure. Okay. Well, what's the temperature? 77 Fahrenheit. It's kind of down low, isn't it? Let me peek around, look around here. We need Fahrenheit. We need water Fahrenheit. Let me snoop around here and see. Gosh, that's way down low. Well, let me draw the 70 degrees Fahrenheit isotherm. I need to know what this saturation temperature is at, no, it's 77 degrees, just a minute, 77. They don't have a 77 degrees. They don't have a 77 degrees, but the pressure is only it's somewhere around 0.4 psi. I eyeball that. It's somewhere between 0.36 and 0.5. It's about there. But see, our pressure is 300. Well, where the heck is 300? Let me think about this. Yeah, it's up higher. 300. It kind of looks like we're in a compressed liquid. They said 300. Am I reading all this right? I think so. So I guess state one is compressed liquid, huh? What do you think? Do they have a compressed liquid table here? I don't think they do for Fahrenheit. I'm looking. Yeah, they do. But they don't go down to 300. The lowest they have is 500. That's okay. That's okay. I think we're in compressed liquid. Now let me keep reading here. I think we've identified state one. I'm going to peek and see. I'm running out of time here, but I'm having fun. Let me see what my answer book says. I got a bad feeling about this, like I'm way off the track or something here. 4, 1, 10. You know what? I don't even have that one. I would have to go back and pull that up. So we're on our own now. I don't have an answer book. Let me just toss this answer book. Don't need it. But now let's see where we're going. State 2 is 15 psi. Got lost again. Now, where the heck was... just a minute. I'm sorry to waste your valuable time here. We were trying to do an English unit turbine.
Yeah,
And we're
15,
not-
15
Yeah, I
PSI.
found it. Yeah, 15 psi, 77. The temperature stayed the same, looks like. See it? Temperature stayed the same, but the velocity or the pressure is 15. Okay, well, we can do that. I'm having all kinds of trouble with this particular problem. I shouldn't have picked this problem, guys. I regret doing this. It's a liquid water turbine. Hey, at least we're on the right track. The water's coming in as a liquid. You know what? It is. In fact, it's a compressed liquid, isn't it? And it's coming in with a pretty big velocity, 50 feet per second. Now the exiting is 15 psi and 77 Fahrenheit. Well, where is 15 psi? Well,
Much
I'll
lower.
tell you what it is, guys. It's in here. It's between 0.4 and 300. So there's state 2. This is an interesting problem. We're entirely in the compressed liquid region, aren't we? We don't even enter the vapor dome. We don't enter superheated vapor. We're compressed liquid. It's a I got lost again. It's a liquid water turbine. It's like they have at the dam, at the Keystone Dam. They have a dam. You've probably driven across it. And down below, the water goes through this water turbine. And there's these big blades, turbine blades, that the water shoots through there. It turns the blades. And those blades turn a generator, an electricity generator, and there's electric wires that leave the dam. And did you know that we get part of our electricity from that dam? It's a water turbine. Well, that was fun. Okay. Now what? Well, we're going to assume this is 0. So you can forget that. We'll assume it's adiabatic. They didn't say anything about heat transfer, did they? No. And this is what we're trying to find. But they did give us this. Let me circle it. It's 4. We got 5.5 minutes left. Who knows? We might make it. They gave us the velocity too, coming in. It's 50. See it? We're going to assume that you don't need to worry about the gravitational potential energy because it's at the bottom of the dam, right? It's going in at the bottom of the dam and it's coming out at the bottom of the dam. So just forget that. And we know what this is. You know what? If we can only figure out the specific enthalpy, but don't we have an equation for liquids that goes like this? Yeah, we do. Now you're used to that equation for gases. And for gases, there's 2 different values. There's a CP and a CV. We've studied that. That's for ideal gases. Now I don't know if I've done this with you, but you can get the change in specific enthalpy for liquids. There's only one value. And for water, we can look it up. Oh, gee, we only have 4 minutes, but hey, you can do a lot in 4 minutes. Now go to the back here and help me. It's going to have to be English, senor. We need the specific heat of liquid water. And it is well, I think I've told you that. I told you this. It's 1 BTU per pound mass per degree Rankine. Well, now wait a minute. If it's constant temperature, it goes in at 77, comes out at 77. Well, that's 0. There is no change in. I think you can cross that term out, guys, because there's no change in temperature. It's an isotherm, right? So what do we have left? We're going to do some algebra now. Guys, I've never done this problem. Isn't this fun? Sometimes it's fun to do stuff that you've never done before. We've got big W dot, doing some algebra, is equal to M dot times VI squared over 2. All the rest of that stuff went bye-bye because the specific enthalpy didn't change, the temperature didn't change. And we know all this stuff. We know M dot is 4. Oh, gee, I only have 2.5 minutes left. It's 4 pound mass per second. That's given. We know the velocity, it's 50 feet per second. Oh, wait a minute, you have to square it and divide by 2. And we're done. Well, not quite. What we want is, we want either horsepower or maybe BTUs per second, or foot-pounds force per second, or foot-pounds force per minute or per hour. We don't have that yet. And we have 2 minutes to convert this. Okay, now here's how you do it. Can I write that up there where I got more room?
Of course.
Let me put this where we have more room. We're trying to find the power of this water turbine. And what we've got so far is 4 pound mass per second times 50 feet per second squared over 2. Hope you can read my writing. Now what we're going to do is a pound force is equal to 32.2 pound mass feet per second squared. Can you see that we can get rid of the pound mass that way? Here, let me cross it out with maybe this green pencil here. See that pound mass? We just got rid of it. Now you see that foot squared per second squared? What that leaves me with is a foot. We can get rid of this. We can get rid of that, but it leaves me with a foot-pound force. And so what we have right now is a foot-pound force, and you could give the answer like that. That'd be okay. Whatever this is a foot-pound force. Foot-pound force. We want it per second. Yeah, see that second right there? This will give you foot-pounds force per second. And I tell you what it is. Oh, gee. Oh, my time is up. Oh, it's so sad. But you could just multiply these numbers and you could get that. And if you wanted BTUs, you have to divide by 778.15. It's so sad, but I had fun. I don't know about you. And you got your homework to do. Do not obsess about a water turbine. I'm not going to give you that. We'll stick with the steam turbines, okay? Any last comments before we say goodbye?
Mr. Griffin?
Yes.
So for the nitrogen, we do not, in the English units, we do not have the table at the back of our book. So how are we gonna
Oh yeah,
draw
I
the
have it in the
PV?
back of. I have it in the back of my book.
And do you know what page do you have in your book? Because I couldn't find the nitrogen table for in English unit.
You couldn't find the English H2O table, Mohammed?
No, nitrogen table.
Oh, well, we're not doing nitrogen.
No, I know. I'm asking for the homework problem. That's what.
Oh, I gave you a nitrogen problem in English?
Yeah, and that doesn't. I couldn't find the table for that.
Okay, well, let me look and see. I appreciate.
That's
I
why
have
I
one.
was having a problem drawing the.
Oh, wait a
PV.
minute. Mine's not in English. Let me look again. Just a minute. I really appreciate you telling me this. I've got ammonia and a lot of other things in English. And what about nitrogen is the question. Gee whiz, Mohammed, I don't see any nitrogen table in English.
Yeah, that's why I was wondering how are we going to draw the PV diagram on that homework problem.
That's going to make it hard, isn't it?
Yeah, because we do not have any values for that.
Yeah, I
did the device sketch.
I don't think we have it.
Yeah, because I did that device sketch on that homework problem, but I couldn't do the PV diagram on that problem because I couldn't find the table.
Yes. There is no nitrogen table in English in the back. So since we don't have a table, you can't draw one, Mohammed.
So I did the device sketch. Yeah, okay.
Don't worry about it. It's okay. Just do the best you can.
All right, thank you, sir.
Yeah, thank you for telling me though. So I'm so glad you told me. Nobody panic over that.
No problem.
Okay, I'm going to say goodbye for now, and I will see you Tuesday at 11, right? I think that's right.
Yep.
See you guys Tuesday at 11. Bye-bye.
Bye. Have a